An ejection seat catapult launches a 200-kilogram mass to 20 meters per second in under 0.2 of a second. This acceleration requires internal gas pressures exceeding 10 megapascals, generated by a primary nitrocellulose cartridge. The catapult consists of 3 concentric telescoping tubes. As the seat rises, the internal volume increases, which would normally cause a pressure drop and a decrease in acceleration efficiency. To counter the volume expansion, auxiliary cartridges fire sequentially along the tube length. This sustains a nearly constant pressure profile, ensuring the pilot experiences a steady 12 to 16 G-force rather than a singular violent spike. Dynamic O-rings and metallic seals prevent gas bypass between the telescoping stages. Any leakage results in a catastrophic loss of exit velocity, potentially failing to clear the aircraft tail fin. Once the catapult tubes reach full extension, the seat is clear of the cockpit, but lacks the energy to reach a safe parachute deployment height. At this precise millisecond, the underseat rocket motor ignites. The rocket uses a solid propellant grain, typically a composite of ammonium perchlorate and aluminum. The internal geometry of this grain, often a star shape, determines the thrust curve over time. The rocket motor must provide high thrust for approximately 0.5 seconds. Engineers optimize the nozzle throat diameter to maintain high combustion chamber pressure while maximizing the exhaust velocity. If the thrust vector does not pass directly through the center of gravity of the combined seat and pilot mass, the seat will tumble uncontrollably. This requires precise nozzle alignment relative to the occupied seat. Modern seats utilize stowable pitch control vanes or gimbaled nozzles. These adjust the thrust direction in real time to compensate for varying pilot weights and aerodynamic forces during the burn phase. To stabilize the seat after rocket burnout, a drogue gun fires a heavy slug that pulls a small pilot parachute into the slipstream. This gun uses a dedicated pyrotechnic charge to overcome high-speed wind resistance. At high Mach numbers, the seat is inherently unstable. The drogue parachute provides the necessary rearward drag to keep the pilot's back facing the wind, preventing high-speed limb flail injuries. An electronic or mechanical sequencer controls the timing of every event. If the seat is at low altitude, the sequence accelerates to deploy the main parachute immediately after clearing the aircraft. Barostatic release units use aneroid bellows to sense atmospheric pressure. They prevent main parachute deployment above 5,000 meters to avoid hypoxia and extreme cold for the pilot. 0-0 performance means the seat can safely extract a pilot from a stationary aircraft on the ground. This requires the rocket to lift the seat high enough for full parachute inflation before touchdown. Before the main parachute opens, the seat must be discarded. Small thruster cartridges push the seat away from the pilot to ensure the parachute canopy does not become entangled with the heavy metal structure. The main parachute is not pulled out by gravity. It is actively launched by a ballistic mortar. This ensures rapid deployment and inflation even in low speed or unusual attitude conditions. The rate of pressure rise in the catapult, known as the onset rate, is strictly limited to prevent spinal fractures. The seat cushion itself is an engineered component designed to minimize dynamic overshoot forces. Before the seat moves, the cockpit canopy must be removed. This is achieved via jettison rockets or detonating cords that shatter the acrylic glass, clearing a path for the ejection in milliseconds. Ejection seat ballistics must function reliably from -55 to +70 degrees Celsius. The burn rate of the solid rocket fuel is temperature dependent, requiring robust insulation and chemical stabilizers. Failure is not an option. Dual percussion primers and redundant gas transfer lines ensure that if one pyrotechnic path fails, the backup path still triggers the catapult and rocket sequence within microseconds. Specific impulse measures the efficiency of the rocket propellant. Ejection seats use high-energy density fuels to minimize weight while providing the massive, instantaneous force required to clear a fast-moving aircraft. Ballistic thrusters pull restraint cables tight around the pilot's legs during the first milliseconds of ejection. This prevents wind blast from forcing limbs outward, which would cause severe joint dislocation. A pyrotechnic reel pulls the shoulder harness tight, pulling the pilot into the optimal upright posture. This alignment is critical to ensure that the vertical G-load is distributed evenly through the vertebrae. Expanding gases from the primary cartridge must travel through a manifold to reach all catapult cylinders simultaneously. Non-symmetrical pressure distribution would cause the seat to tilt and jam in the rails. The seat slides on rails coated with specialized low-friction materials. Even a slight increase in the friction coefficient due to ice or debris can significantly alter the exit velocity and trajectory. Mild detonating fuse or gas transfer tubes carry the ignition signal at velocities exceeding several kilometers per second. This allows for near instantaneous communication between the trigger and the various ballistic components. The dynamic load factor accounts for the rapid application of force. Because the catapult fires so quickly, the structural stress on the seat is higher than a static load of the same magnitude. During the half-second burn, the rocket nozzle throat experiences extreme thermal and mechanical stress. The material must resist erosion to keep the internal pressure high enough to maintain effective thrust. The nozzle uses a convergent-divergent geometry to accelerate the exhaust gases to supersonic speeds. This conversion of thermal energy into kinetic energy provides the necessary impulse to lift the seat. Pyrotechnic charges are hermetically sealed to prevent moisture ingress. Water absorption would degrade the propellant, leading to inconsistent burn rates or a complete failure of the ejection sequence over time. Modern digital sequencers use solid-state gyroscopes to detect the seat's orientation at the moment of ejection. This data determines which steering rockets to fire to bring the pilot to a stable attitude. At supersonic speeds, the aerodynamic center of the seat shifts significantly. The ballast and rocket thrust must compensate for these shifts to prevent the seat from pitching violently into the wind. Small pitot tubes on the seat measure the airspeed immediately after ejection. This information is vital for the sequencer to decide whether to use high-speed or low-speed parachute deployment modes. Some aircraft use linear-shaped charges to cut through the canopy frame. These focus explosive energy into a thin jet of metal that slices through thick structures in microseconds, ensuring a clean exit. The barostatic lock is a failsafe that prevents the pilot from being separated from the seat too early. It ensures that oxygen systems and heat shielding remain available during high-altitude descents. The entire sequence begins with a mechanical strike on a percussion cap. This impact creates a small flash that ignites the booster charge, starting the chain reaction of the catapult and rockets. To supplement the drogue parachute, some seats deploy mechanical flaps. These increase aerodynamic stability and provide a more predictable drag profile, reducing the complexity of the rocket steering requirements. As the solid fuel burns, the surface area changes, which alters the thrust. Engineers design the grain to be progressive, providing more thrust as the seat accelerates to counteract increasing aerodynamic drag. The rocket motor casing is lined with an ablative insulation layer. This protects the structural integrity of the seat from the 2,000-degree combustion temperatures during the critical half-second of flight. A small pyrotechnic actuator opens the emergency oxygen cylinder the moment the seat leaves the cockpit. This provides the pilot with breathable air during the high-altitude phase of the ejection trajectory. When the main parachute inflates, it creates a massive opening shock. Ballistic reefing cutters delay the full expansion of the canopy, allowing the energy to dissipate over several stages of inflation. The rocket nozzles are often angled to throw the seat slightly to the side. This prevents two seats in a tandem cockpit from colliding and ensures they follow divergent paths for separate parachute deployments. Before the flight, the seat height is adjusted using a gas actuator. This ensures the pilot's eyes are at the correct level, but the system must be locked rigid during ejection to handle the G-loads. The sustainer rocket is usually a multi-nozzle manifold curved around the base of the seat. This compact design allows for maximum fuel volume without interfering with the seat's fit in the narrow cockpit. Detonating cord travels at nearly 7,000 meters per second. This speed is essential to ensure the canopy glass is completely pulverized before the seat has moved even 1 centimeter upward. Small timed explosive cutters slice through the cords holding the parachute closed. This sequential opening prevents the pilot from experiencing a lethal jerk during high-speed parachute deployment. At low altitude and high sink rates, the rocket sustainer provides a lofting maneuver. This converts horizontal velocity into vertical height, buying the parachute enough time to open before the pilot hits the ground. Seat rails must withstand the enormous bending moments during the catapult phase. They are manufactured from high-strength steel or titanium alloys to ensure they do not deform under the off-center loads. The Environmental Sensing Unit integrates altitude and airspeed to select from multiple pre-programmed ballistic sequences. This optimization ensures a safe recovery whether at sea level or 30,000 feet. The entire ejection is a problem of kinetic energy management. Ballistics provide the energy to escape, while the parachute and aerodynamic drag work to safely dissipate that energy before ground impact. Safety pins and interlocks prevent accidental firing during maintenance. These mechanical blocks must be removed by the pilot, often via a pull handle, to arm the ballistic firing chain for flight. Each stage of the ejection depends on the successful completion of the previous one. This serial dependency ensures that the rocket cannot fire while the seat is still inside the cockpit structure. The ballistic performance defines the recovery envelope. Outside these limits of speed and altitude, the physics of the system cannot overcome the combined forces of gravity and inertia to ensure pilot survival. The rocket casing must be light, yet strong enough to contain high pressures. Engineers use hoop stress calculations to determine the minimum wall thickness of the cylindrical combustion chamber. An ejection seat is a masterpiece of precision engineering, where ballistics and rocket technology work in a choreographed sequence to save a life in the most extreme mechanical environments imaginable.